Let us now look at what is the OR gate. The OR gate is concerned with the output that will result in a binary 1 or true if at least one of its input is true. We have input A and B. If one of them is I or both of them are I, the output will be true. So you can see from the symbol of the OR gate and the package view, and similarly we have the physical component, and this physical component can be identified by the number 7432. So we have 1, 2, 3, and 4 OR gate inside the 7432 package. Let us see from how it was constructed. We have a transistor circuit that forms the OR gate. So I will draw the diagram, and this is how a transistor made up the OR gate. We have two NPN transistor. So when we say when one of its input is true or both of the inputs are true, the output will be I. We have the resistor emitter here. Previously we discussed that if the current is flowing through a transistor or any conducting material, the current will always choose the path where there is less resistance. Therefore, this resistor emitter here normally acts as a resistance to the ground to avoid the flow of current in that region. So the current will always flow in this region when the conditions are true. So we have 2 to the number of input, which is 2, will give us 4 combination. We can draw up the truth table based on the condition. If both input are 0, logic low, the output will be low. If one of the input is I, for example, this is one of the input and this is another input. If one of these input is high, that means the output will be I. And also when both inputs are high, the output will be high. Let me as well draw the equivalent switch circuit for this case. Therefore, we can now see what is really happening with regards to the switch current equivalent circuit and the transistor or gate construction. So when both input are 0, that means if we apply 0 volts, that means this switch is open and this switch is open. So no current will flow through this region. And this is also open. So the output will be low. And when we have in the second combinational set, if we apply 0 volts to input A and positive 5 volts at input B, that means the switch B is closed and we can say no current is flowing in the first NPN transistor, and now we have current flowing in this direction. So we can see that the current can reach the output. So the output will be on in that case. So the light bulb is now on. This is for the second combination. And for the third combination, we can also see if we apply positive 5 volts at the input A and apply 0 volts at input B. That means this will be closed and input B is like a switch open. In that case, no current will flow in the second transistor. The current will flow from the transistor. Since the emitter of each of these transistors is connected to the output, the current will now flow in this direction. So the output will be high. Similarly, this light bulb will be on. therefore it is given as 1. And finally, if we have both the input having 5 volts, that means both the switch is closed, therefore the current will flow in the transistor A and transistor B to reach the output, so the output will also be I. This is how they design the OR gate. So imagine if you want to see how many transistors build up this 7432 package, we have 2, 2, 2, 2. So a total of 8 transistors that make up the OR gate. So I hope you can be able to understand now what is a OR gate. And if we look at the application, so considering the two rooms that we discussed previously, room 1 and room 2, we have the air conditioning system. In the previous AND gate, we described that both rooms must have temperature greater or equal to 30 degrees in order for the air conditioner to supply the cool air to those rooms. However, in this case, if one of the room, example room 1, have temperature greater than or equal to 30 degrees Celsius, room 2 we have temperature less than equal to 30 degrees Celsius, then the air conditioning system will only provide cool air to room 1 and not room 2. And it is the opposite. If both of them have greater than or equal to 30 degrees Celsius, then the air conditioner will supply both rooms with cool air. And in case where room 1 have temperature less than equal to 30 degrees Celsius, then only room 2 will receive the cool air while not the room 1. In case where you want to design a system with such condition, you can mostly choose between the logic gates to enable this process. And I believe with this example, you can now be able to clearly understand what is a OR gate, so you won't be able to confuse later on in the future. And finally, we can represent the OR gate mathematically using arithmetic. V out is equals to input A plus input B. So this is the binary arithmetic. So it will be responsible for adding binary ones and 0. The only difference between binary, if you have 1 plus 1 will give you 1 and not equals to 2, because the output will only have one of the state, 1 or 0. Therefore, the output will be 1. Next, we should be able to look at a NOT gate. So what is a NOT gate? A NOT gate is also called an inverter. That means it normally inverts the signal. Basically, the output will be the opposite of the input. If the input is true or having logic 1 applied to this particular NOT gate, the output will be false or low. So from the symbol, we can see from this small sign which says inverted, and you have the physical component and the package view. So it is different in which you have 1, 2, 3, 4, 5, 6 set of inverter inside this particular package of the NOT gate, and the number that identify is the 7404 IC chip. Let us see how we can construct using a transistor for this particular NOT gate. And this is now the transistor for the NOT gate. So we have the R base, the resistor connected to the source, you have the ground and the V out. This is the resistor base in which it limits the flow of current. You don't want huge current to pass through the base of a transistor. We only care about a huge amount of current flow from the collector to the emitter. So the current from collector to emitter can be large. And from this base, we only need a small amount of current to switch on this particular transistor. Therefore, we have the resistor base connected from most of our circuit. So since it is an inverter circuit, let's draw a truth table that will represent the operation. So 2 to the number of input, we have 1. So we have 2 combination, and we can have A and A inverted. So we have now 0 or 1. Since it is a simple inverter circuit, we can agree that if the input is 0, the output will be 1. And if the input is 1, the output will be 0. Simple as that. We can also draw the equivalent switch circuit. So the equivalent switch circuit for the NOT gate. And now this is the equivalent switch circuit for this particular NOT gate. So it is configured differently based on how we design using a transistor. For example, if we apply 0 volts at the input, this transistor will be off, and current will now flow from 5 volts to the output, and the output will be on or having positive 5 volts. Similarly, if the switch is open, that means the current will follow this path and it will light up the lamp. In the other combination, what will happen if we apply positive 5 volts at the base of the transistor? That means this particular circuit, the transistor will be on. Therefore, the current will now flow from collector to emitter. Since both of them are having low resistance, why is it not flowing through the voltage output? Because the Vout in an actual case, it is connected to the load, because this particular gate is preferred to drive a load. And when the transistor is switched on, this path becomes a low resistance. Therefore, a current will flow in this direction and not in this direction. Therefore, this region will be off or having 0 volts. Similarly, if you see from the switch diagram, if the switch is closed, therefore this is the load, the lamp. Therefore, the current will now follow this path to the ground, because the switch and the ground have 0 resistance, and current will choose this region. So this is how they design a transistor for the NOT gate. Therefore, the mathematical equation can be that say Vout is equals to A equals to A inverted. And in case of the application mostly describe where can we use this NOT gate, or where NOT gate can be applicable. Let me give a different example. So we have emergency shutdown switch. For example, a ship. The switch can be located at the bridge of the ship, and this switch is responsible for controlling the movement of the blade, and it is connected to the power supply of the ship. If there is an emergency where they need to automatically switch off this particular engine, then what will happen? They will just have to press this switch to allow the motor or the engine of the ship to shut down in case of an emergency. By pressing this switch, all the power will be grounded and this will not work. So this can be seen as an application in which we can be able to use the NOT gate. When the switch is closed, that means the blade will not work. When the switch is open, the blade will work. So this can be a simple application that can describe the operation of the NOT gate. So we will move on to describing another logic gate. If you like our video, you can kindly like and subscribe to our channel to support what we are doing to help you learn more in terms of a digital system.